Okay guys, let's take a look at our lesson for today. This is on the squeeze theorem. I really prefer squeeze theorem. Okay, so probably you might not be surprised to know that I love calculus textbooks, and I have a lot of them and I like to read them. I mean, what would be more fun, right, than reading calculus textbooks? I mean, it's fun. And different textbooks call this theorem different things. I mean, I've seen the sandwich theorem, and that seems kind of boring. It's like, what kind of sandwich? Why would you call it the sandwich theorem? But at any rate, I like the squeeze theorem. I like that name. So I just want you to know there could be other names that you might see, but this one is my favorite. So let's talk about when we would use it and what is it. Basically, we use it with limits. And so we would let f, so I'm going to read through the theorem itself. So f, g, and h are functions that satisfy this inequality. Okay. Now sometimes you're going to be given the inequality. That's kind of nice. And sometimes you're going to have to create the inequality. And I have an example of each type, where you're given the inequality and where you have to create the inequality. So f is smaller than g, which is smaller than h. Okay, so we have this inequality going on. For all x in some open interval. So that's going to be true in some interval that contains this number, the number a. So in this, you can see in this picture right here, here is a right here. It's an x value, some particular x value, with the possible exception that the inequalities need not hold at a. So maybe they hold except for at a. If f and h have the same limit as x approaches a, then, so let's see what they're doing. They're setting up the squeeze theorem. They're setting up the squeeze. They're saying if the limit as x approaches a of f of x, so this piece, is equal to the limit as x approaches a of h of x, which is this piece, they both equal the same number, then the middle guy gets squeezed in. He's going to be the same number too. This theorem is helpful when this g of x, this middle guy right here, or in this case, yeah, that should say g. That should say g. It's helpful when g of x is maybe something that's really hard to work with. Maybe we can't pin it down. Maybe it's hard to do the limit of it. And we would rather approach it this way. So this is with quite difficult things. And so this is a visual picture of what that inequality looks like. So we have f of x is the smaller one. That's this green one. G of x is in the middle, and then h of x is the one that's the greater one. And so that's the kind of scenario we'll be looking at. What we're doing is we're narrowing it down so that we can, basically pin down the middle one. What is it? What is its limit? Does that make sense, what we use it for? Okay, any general questions about the concept before we go to the examples? Okay, so the examples on the next page, like I was saying, we're going to do one where the inequality is given to you. That's the first one. And we're going to do one where you have to find the inequality. All right, so let's take a look at the first example. Notice we have an interval here for all x that basically are in as element of this set, -1 to 1. So this inequality only works between -1 and 1. Outside that interval, there's no guarantee. This is the inequality that we have set up. So in this case, they've given us the relationship between h of x and the other two functions. They've already told us that this one is smaller than h of x, which is smaller than this one on the interval -1 to 1. So they're asking us to find this limit as x goes to 0. The first thing that we just need to make sure, it's just good practice too, is this number in the limit, in this? I mean, is it inside that interval? Not that I've seen them intentionally try to trick you before, but it could happen. I mean, this is going to 0, and that number is inside this interval, so we're fine. We're okay. We can use this inequality to help us find this limit. All right, so they want us to find the limit as x goes to 0 of h of x plus 25. All right, well, let's investigate this inequality over here, this limit. So I'm going to take the limit. I'm going to use the squeeze theorem. I'm going to take the limit of this left side, the limit as x goes to 0 of the square root of 8, let's see, x to the 8th plus 7. I substitute a 0 in there, and I get the square root of 7. Okay, now I'm going to take the limit of this right side, going to 0. So the limit as x goes to 0 of the square root of 4x to the 8th plus 7. And so I substitute a 0 in, I solve my limit, and I get the square root of 7. Since the smaller function tends to square root of 7, and the larger function tends to square root of 7, then by the squeeze theorem we can prove that the middle function is going to tend to square root of 7 at x equals 0. Okay, and that's how we use the squeeze theorem. So we would say, therefore, by the squeeze theorem, and yes, you do need to name it. I mean, we are all some great mathematicians in here, and we could say because I said so, but we really want to use the theorem, right? The theorem, and that because it's been proven, it's a valid theorem. So by squeeze theorem, the limit as x goes to 0 of h of x equals the square root of 7. Okay, so now we know what that limit is. Now let's do the final thing they asked us for, is to find this limit. I'm going to rewrite it using limit laws. You don't have to. I mean, you could go straight to the answer if you want to, but I'm going to just rewrite it using a limit law. So the limit as x goes to 0 of h of x plus the limit as x goes to 0 of 25. We know this limit is the square root of 7, and we know the limit of a constant is constant. So this is our answer. Okay? How are we with that? All right, great. On this last one, we are asked to use the squeeze theorem, and they didn't give us any kind of inequality. Now, I will tell you that a lot of times, this happens with trig functions, because we really can bind many trig functions in naturally. I mean, we know that sine of anything, of any number, is going to be between -1 and 1. Notice there's no double angle, there's nothing going on, it's just plain old sine. Sine of any number is going to be between -1 and 1. So when we are asked to come up with the inequality ourselves, we need to start with something that we know. All right, we know that sine is between -1 and 1, and so that's what we're going to write. So sine of 1 over x is between -1 and 1. So we're going to start with something that we know. And then we compare what we know to what we're asked where we're supposed to go. We're supposed to get this guy right here. X sine of 1 over x. Okay. So what we would do is we're going to, I call it layering on. We're going to layer on other numbers or functions. If I multiply everything by an x, I'm going to get this. Now we're going to talk about that in just a second. Let me do that first. If I multiply each of these individuals, the whole thing through by x, now we need to address this before we move on. We need to address it because we have a couple of options. We can either restrict the domain to make this true, or we can put absolute value bars here. Those are our options, because this in itself, this expression itself is not true if x is negative, right? Because if x is negative, then, and this I explained this earlier today, and students were very confused, so please stay with me here. I can multiply through by an x, and that's all well and good, as long as x is positive. But if x is negative, this is an untrue statement. Because if I put a negative number in here, a negative times a negative makes it a positive, right? And is a positive number less than a negative number? You see how it messes it all up? So you have a couple of options in order to fix this. You can use absolute value bars. That will fix it. That forces the value you put in there to be positive. Or you can restrict the domain. It doesn't really matter, whatever you like to do. And if you forgot to do that, you probably would not lose any points if you forgot to do that little nuance, but I need you to understand that this is really not an accurate saying right here. Okay, so I'm going to just restrict the domain. I'm going to say that x has to be larger than 0. Okay, it has to be positive for this inequality to work. Okay? Instead of using absolute value bars. You can use absolute value bars if you would rather. Alright, so we have the squeeze set up. Now what did we do on this one? Once this inequality was set up, we did the limit of each side, right? That's what we want to do here. We're going to do the limit of each side. So the limit as x goes to 0 of negative x, so I substitute a 0 in and I get 0. And the limit as x goes to 0 of x, substitute a 0 in, I get 0. Now notice that I'm going to get 0 whether this is negative absolute value of x or negative x. Right? We comfortable with that? We're still going to get 0, no matter which way I decide to write it. Since this is true, and this inequality is true, I can say, therefore, by the squeeze theorem, the limit as x goes to 0 of x sine 1 over x is 0. And that is an example of how we would do the squeeze theorem if we had to set up the inequality. Okay? Yes?
I'm not very satisfied with that proof because if you're assuming x equals 0, then that means you can only do that one side again if you plus.
So we could look at the graph to verify. It would probably be better to graph it if this is not making you happy. We could graph that to verify that that's true. So I would do that. I would graph it. Okay? Yes? Right. X sine 1 over x. Yes, I multiplied the whole thing by x. Uh-huh. I have a little, that's an x. That's a weird looking x, but that's an x. Yes? Yeah, the other way that I've seen this written is with absolute values. And if that's a happier thing for us, we can put the absolute values, and that'd be fine. Yeah. Okay. Any other questions? All righty.